very small. There are many open questions, and my motivation are very old. They come from a postdoctoral position in Bonn with Sergio Albeverio, where I learned infinite dimensional integrals, and I saw that there were some things that were, let's say, made as people can, you see. So there were many geometric gaps. So I tried to think about it, but as I said, I am not a specialist of these topics. So the Feynman-like integrals, I know them, but I am not in this I cannot go in the details in this topic. So I try to construct some things which were with respect to my knowledge. So I will explain the organization of the notions that I will give. First, I think that I need to explain what are diffeologies, what are they done for, and give some examples that I will use after. Then these diffeologies, I will first apply them to probabilities. So on probabilities, there are existing ways to differentiate, since it is the problem of diffeologies, make a safe differential geometry. So there are some ways to differentiate. I do not wish to be exhaustive in the presentation of the way of differentiation on probabilities, but I will make some links with some existing topics. This leads to what I call vague diffeology. It is a topic which is used often, and a new diffeology called Monte-carlo diffeology. And then I will extend these diffeologies to spaces of means, and with motivation, normalize infinite dimensional integrals, on which I will finish with two examples on the space of connections of a principal bundle with a compact base and compact structure group. Then, what is a diffeology? So, naturally, in differential geometry, the manifolds that we consider carry an atlas with charts, which enable to say locally what is differentiable of k times differentiable of smooth. And there are some examples of objects that do not carry an atlas. So we have to say how we define smooth objects. And the idea by Chen and Suryo is to define parametrizations of the space. That is, maps from an open set of an Euclidean space to the set X, which are said to be smooth. So, of course, for this definition, we need some let's say, compatibility conditions. So there are three. The first one is the covering, that is given, every constant function is in the set of parametrization. Locality, that is if you have locally smooth maps, then they are smooth maps. And smooth compatibility, this means that it is compatible with composition with smooth functions. So with all that, when we have a set of parametrizations which satisfies these three axioms, we call it a diffeology. And a set X with a diffeology is a diffeological space. So clearly, with this setting, we can do many things that we do in classical differential geometry. That is, we have cotangent spaces, differential forms, the Ram cohomology, singular cohomology, symplectic geometry. It was one of the motivations of this setting. We can define also with more problems tangent spaces, and we have good formulas for the calculus of variations. We have Riemannian metrics, pseudo-Riemannian metrics, and in fact, the properties are actually to be discovered because it is quite a new topic. So I will mention some examples which are only from this year and which are crucial in order to understand clearly what happens. So it is my motivation make differential geometry for this talk on spaces of diffeologies, integrals, infinite-dimensional integrals, well, in a way that has to be explained. So what do I need for this? I need some examples of diffeologies, and I need to precise what are the properties that I can use, that I will use. So examples. When you have a family of diffeological spaces, finite, countable, or uncountable, there is a product diffeology. When you have a diffeological space and take a subset in the diffeological space, you have a subset diffeology. And when you have a relation, an equivalence relation on a diffeological space, without restriction, you can take the quotient and have the quotient diffeology. So it seems very, very nice, and even nicer when you have any finite or infinite dimensional manifold. When you take all smooth functions from an open subset of an Euclidean space to this manifold, it gives you a diffeology called nebulae diffeology. Nebulae because it is somewhat the maximal one, which describes the geometry of the manifold. Then this nebulae diffeology can be extended only considering a set f of functions from x to r. So now take the set f of functions. You assume that the parametrizations composed with any function f in f gives us a smooth function. These spaces are called Fröhlicher spaces. So these are restricted classes of diffeologies. The comparison has been done by myself in 2006 and completed in 2012 by Jordan Watts. Then there is also we need also a functional diffeology. What is this? When you have two diffeological spaces, then we can define smooth functions. That said, smooth parametrizations to smooth parametrizations, a very natural property. And this full space of smooth functions from x to y has a natural diffeology, and it is called functional diffeology. It is the diffeology for which the evaluation maps are smooth. So of course there are some other properties, but this is this property which is of interest for me here. Then when we have an algebraic structure, for example, a vector space or an algebra, we call it diffeological if the operations are smooth. So we can talk about the smooth dual space, and we can have a diffeology on the smooth dual space by the functional diffeology. And the pairing is smooth. Finally, I need also a diffeology on Cauchy sequences. So now I take a target space Y, which is complete, and I assume also that it is diffeological. That is, the plots are continuous with respect to the plots of the diffeology. So in this target space, I take a subspace X. I assume smooth inclusion. It does not mean that it is the subset diffeology, you know, but smooth inclusion is the only necessary property. For example, think about the inclusion of Q in R, or think about the inclusion of smooth maps into C0 maps, for example. So I can make Cauchy sequences for the metric in Y, but with coefficients in X. It is the space that I'll note as C of X, Y. On this space, since it is a subset of X power n, I can take simply the subset diffeology of the infinite product diffeology, but the limit is not smooth for this diffeology. So I have to restrict the possible parametrizations and ask also that the limit in Y is smooth.
Jean-Pierre, Daniel, Bettina has question. Can you repeat question to Jean-Pierre?
Yes. Okay. Question. Okay. So
the question. So please, Daniel.
Okay. Completeness. Okay. Yeah. So here there are two structures. First, there is a structure of metric space. For this metric space, I can define completeness. And then I add a diffeology on this metric space, assuming that all the parametrizations are continuous with respect to the topology, the metric topology. I think that it is maybe it is more clear. Well, you are welcome. So with this set, in fact, this Cauchy diffeology, I have to say a little more words about that, because it seems central in many fields in numerical analysis by when you try to approximate solutions of differential equations. So it was the goal of the paper that I mentioned here, and in fact the Cauchy diffeology that I will give later is just given in an example of this paper.
One more question, Jean-Pierre. So the notion of the diffeology is notion of smoothness. And complete, that means topology. So you silently assume that you have the compatible topology. And actually, you mentioned about the metric, yeah, Cauchy sequences.
Yes, yes. I do not want to really to go to topological problems. So it is why I only assume that there is a topology in Y, which is in some sense compatible with the diffeology. It is the point. Of course, there is a notion of D topology related to a given diffeology, but in fact I do not need it. And even more, for this D topology, I am not sure that this D topology can define some Cauchy sequences, even if Cauchy sequences and the notion of convergence of Cauchy convergence can be refined in when the diagonal is closed and so on, but it is really not clear. The notion of D topology is defined, but we do not know its properties, in fact, except in trivial cases when it coincides with the classical topology. For example, in Rn, the D topology is the topology of Rn, and that's all. So here we can say some things, but after there are many open questions on that notion. So it is the reason why I avoid this question.
Okay, thank you.
Then, okay. So let me turn to spaces of measures. So when you consider Radon measures on manifolds, then Radon measures are already dual spaces. So it is somewhat well easy, and it's an easy exercise to define their diffeologies. And one way which is even more safe is to consider smooth functions instead of C0 functions. So sorry, there is a misprint here in the second case. I need compactly supported smooth functions.
You can correct it and give me later.
Sorry?
you can correct it and send me after your lecture.
Oh, okay. Thank you. So what I want is that the integration of function is smooth in the product. Radon measures times smooth functions. You see, and you can reduce this first approach to the probabilities on M. So it is what I call vague diffeology. So this is typically what we can find in works on differentiability. So when you look, for example, at the book by Bogachev, differentiable measures and the Malevin calculus, it is one case that he considers others, of course, but he considers also this one, that is, he calls it a duality approach, that for the duality, for some kind of weak star topology, then we have some convergence of a limit that I wrote. So in this approach, I have to say that we are not exactly in the diffeological case. That is, in this work, the limit needs to exist in the space of probabilities. And on diffeological spaces, vector spaces, it is not so obvious that the tangent space at one point is in the vector space. For example, Christensen and Wu gave an example in their last paper published in Israel Journal of Mathematics. They take R2 and they produce a diffeology for which the tangent space, defined by smooth paths, has an uncountable dimension. And it is a diffeology which is very natural. I used it, I mentioned it, and in the early papers by Suryo and by Iglesias and so on, it is considered also in some examples. So the problem of the tangent space is not so clear, and there is no problem apparently when we consider the nebulae diffeology, but it is only apparently, I cannot prove it for the moment, nebulae diffeology, and assume that there is some completeness on the topological vector space. But these are the classical conditions, in fact, for a good behavior of differentiability. So here there are some open questions. We can define some diffeologies, but the differentiation of a path may lead to problems if we want a value of the kinematics, in fact. So this approach is also used on sequences of Dirac measures. So there is a series of work by Albeverio, Kondratiev, and so on, by considering locally compact, non-compact manifold, and considering Dirac measures which are locally finite. And it is inspired, I think, by other works. And I found also in the book of Ismaginov the same procedure on S1, but he considers sequences of Dirac measures with one accumulation point. So it serves as in the realm of representation theory of infinite dimensional groups. And while Albeverio, Kondratiev, and so on make differential geometry for let's say Gibbs measures, and the different differential forms, Laplacians, and so on. So these are approaches where of course the word diffeology is not present. They are using what is called Sikorsky space, but the approach is the same. In fact, from the Sikorsky space, you can define a Fröhlicher structure, which is equivalent. Differentiability is equivalent. So in the existing literature, we already use this approach. So
do you mean that diffeology defined by dual structure is not compatible with the differentiability defined by Bogachev?
There are some open questions, I would say.
Okay, so that's very interesting. We should how to say,
yes,
later.
Yes, in fact, I think that in the second example, why is it developed? Because it works. You know, we can do it because it is safe. We see the points of the Dirac measures, so we can have a geometric intuition, and the things are running well because of this simplification. But I will speak about this approach in my next slides, because this approach contains a nice idea, the idea to approximate probabilities by Dirac measures. It is the Monte-Carlo method. So let's say that I have a compact manifold because I want to stay in the playground that I know, you know. So the Monte-Carlo method says that any probability it can be approximated by barycenters of Dirac measures, and when M is compact, there is a nice metric called the Prokhorov metric, for which the space of probabilities is complete. So we are exactly in the setting that I used for the Cauchy diffeology. That is, my space X is the finite subset of M. So I identify it with Dirac measures, and then I take the barycenter with equal weight, and then I take yi as the space of probability in M. So of course, for probabilities in M, we already have a diffeology. And we can consider the Cauchy diffeology on P of M, which is stronger than the VAG diffeology. That is, we assume that the sequences of Dirac measures are moving smoothly also. So there is here a vibration. As a total space, we have the Cauchy sequences. As a base space, we have the probability measures, and the projection is the Cesaro mean. So it is it is an open direction for investigations, because, as I said before, this vibration also appears in many numerical schemes. So knowing more about it would be interesting to have some let's say geometric indications on the problems that we consider that can be very different from one to another.
Jean-Pierre, so C, B, theta, F, N, M, P, and M, that means that space upon smooth mapping, yeah, from the
sorry, I did not understand what
you may hear that's a space up on smooth mapping from beta F N to space up probability measure on N, right? So that's a probability measure. You have diffeology from each diffeology, because there are a lot of diffeology. You take the diffeology of the dual space because the N compact, yeah? So
yeah.
I see, and that so you fix that the diffeology and the projection. I do not. What is Serraro mean?
I think that I see the point of your question. So here on PF there is only the diffeology of product.
Yes.
On P of M,
yes,
there is the vague diffeology.
Yes.
And on C of PF and M,
yes,
it is not the product diffeology, because I assume also that the Césaro mean needs to be smooth. So I take some restrictions on the plots. Was it the point that?
Okay, so that is some technical question. I should ask you later.
Okay. So so with this picture, in fact, we see that we have sequences of probabilities that, in some sense, are lead to some diffeologies on the space of probabilities. And this picture can be generalized. That is, here in the Monte-Carlo method, we know that such a convergence exists, and we know the existence of the sequences of Dirac measures. But when we turn to more general settings, then we can make the same procedure. That is, we can consider sequences of probabilities for a family of functions, then the evaluations converge. I call it probability means. Then, as a special case, we can take Dirac means. And with these constructions, we can always construct a duality or a Cauchy diffeology and a vibration. But here, from this viewpoint, it depends on the space F that we want to integrate, in fact.
Jean-Pierre.
Yes.
The probability means with respect to F. So that means that you fix some measure of, but now I see you sequence of probability measure. So you have sequence of probability measure and family of function. So
yeah, it is the problem. Your point is exactly the point of this construction, because when you take such sequences, you do not get measures. you get means. What is a mean? It is only a linear functional,
Yes.
which for which when you evaluate it at the one function, which equals to 1 at any time, then the mean is 1. And then it is what we are going out of the realm of measures, and then we go to the realm of amenability, in fact. And in this approach, we can construct diffeologies too. So why do I want this? It is the point. Let me give first the example, the first examples. Consider finite dimensional oscillatory integrals. Then on Rn, you need an exhaustive sequence of compact subsets, and then assume the convergence. It is the point here. So now look at the sequences that I give. Consider a measure with infinite mass mu, and consider the sequences tilde mu n. Then, in order to define it, you need an exhaustive compact sequence of compact subsets of M. That is, the sequence is increasing, and the union of the Kn is M. And then, since we have a sequence of probabilities, we can apply the procedure. So here, I have a diffeology which applies to, let's say, with some mild changes, it may apply to Fresnel integrals, and which are not measures, of course. And with this procedure, one remark is that oh, sorry for the misprint again. We have when we consider a Lebesgue measure, we can replace mu by lambda, and then make the same procedure, and the mean that we get, it is a mean. In fact, total mass is 1. The mean that we get is translation and scale invariant, and it is invariant. If you choose well also your sequence of compact subsets, you can show that it is invariant also by rotation. But actually, this Lebesgue mean depends on the compact sequence on the sequence of compact sets. That is, if you want to have an idea, in fact, when you take a compactly supported function and evaluate it by this mean, then the mean is 0. And we are pushing the mass at infinity. So I think that at the horizon there are some things that happen. I think that it defines some things. It defines something, let's say a mean at the horizon. But this is again an open question. So once we have done finite dimensional integrals, let's move to infinite dimensional ones. So So I want just to specialize now to an infinite dimensional diffeological vector space, and I take an increasing sequence of finite dimensional vector subspaces. I say that separate V, that is, I could say that the union of Vn is V, or dense subset of V, let's say. So why do I assume that? I want to make cylindrical approximations. That is, I take functions which are defined in Vn, and I expand them into V. Just saying that it is constant on the complement of Vn. So here we can have probability means, but we can have limits of means. It is why I need a bigger class that I call limit means. Few examples before a big example. The first example on the Hilbert cube. So I take the restriction of the Lebesgue measure to the interval 0, 1. I take the countable power. We all know that it is a probability. So, okay, it is to fix the ideas, and we can have a Monte-Carlo sequence and so on. But let's say that the basic example of Daniel integral is in this class of examples. Now take V equal to R infinity, so the union of Rn. We can also ask to have a Hilbert space instead. We take a measure mu on R, take the products, then it defines an infinite dimensional mean, and the special case of mu equal to lambda is the famous formal infinite dimensional Lebesgue measure, which is in the formulas of the Feynman-Cauchy integrals. But but we say formal, you know, because it has very few finite measure subsets. But so in order to repair it, and it was my motivation, in order to repair it, when you look at the Feynman-Cauchy formula, you have this integral with respect to the infinite dimensional heuristic Lebesgue measure, but it is normalized by the volume, which depends on the action functional and so on. So the idea is to insert this normalization in the sequence, and with this normalization, then we get infinite dimensional means and infinite dimensional, in fact, Feynman-Cauchy integrals. So, of course, there are some things to say. That is, the action functional. For the action functional, with this picture, we need to make weak rotations. That is, for this picture, it seems very technical to make oscillatory integrals, and but through weak rotations, in many cases we have a positive action functional, which means that we are in the good class of example.
Oh, just Jean-Pierre. So that means you get new example, a new construction of a four-mean differentiable measure on infinite dimensional space.
Yes, I will come to differentiability. Please.
Okay.
So I will come to differentiability, because here I wanted to highlight first the examples that we get with such a construction, because I think that we are not so far from examples of interest. But now consider the full space of such limit means. Then if we fix some spaces of functions which needs to be integrated, then we have a total space F as before. Let me just come back here. I assume to have a family F of functions that I need to integrate, and it is typically what we need here to get a space of means of normalized integrals on which we can differentiate. We need then to fix the space of functions which needs to be integrated and which will be our test functions. So this is the step where, for the moment, in my investigations, I stopped, because these functions have to be defined, I think, from one model to another. So it is a big point. But here, technically, we have the tools to differentiate some families of infinite dimensional integrals. Then the example which I developed. Consider now the space of connections of a compact principal bundle. So here it is an infinite dimensional vector space, and we can approximate the connections by many ways. It is the problem.
Jean-Pierre, sorry for interrupting. So the space of connection on compact principal bundle, that means you consider a principal bundle of the group, a compact group action. Yes,
the full space is compact. This means that the structure group and the base needs to be compact.
Base compact. So the base is a diffeological space of the measure.
Oh,
what is the base here?
The base is a finite dimensional compact manifold.
Infinite dimensional compact
finite dimensional compact manifold.
Finite dimensional compact manifold.
Yes. Yes.
Yes.
I can.
So thing is still have the classical.
Yes, it is classical because here the things have to be clarified. In fact.
Okay. Thank you.
Really there are things to be clarified, and it is the point that I want to highlight, because on this space of connections, then when you discretize the connection, the classical way to discretize the connection is to use a triangulation of a base manifold, and And in general, people ask the principal bundle to be trivial, or they cut it along the cut locus of the base in order to have safe things and say that it is trivial anyway, and have some conditions at the border. But we are on a triangulation, and we assume that we have a piecewise affine approximation. That is, it is H10 projection. H10, it is the Sobolev space. And it is typically the Whitney approximation. It gives H10 approximation of smooth connections, and refining the triangulation, then we approximate more and more clearly the initial connection. So with this picture, it defines a sequence of finite dimensional subspaces of the H10 connections. So it is a Hilbert space. And in this Hilbert space, then we can make some cylindrical approximation of Feynman-Kac integrals, and make some well, I called it Lebesgue-like infinite dimensional integral, but well, anyway, it is useful because, for example, for using Chern-Simons theory, we get true formulas for abelian Chern-Simons theory. We get true formulas for linking invariance. So it is useful, but it happens that it is not exactly it is only one example of what can be done, because when approximating a connection, we can approximate it also by holonomy elements. And it is the approach by quantum gravity, which considers only discretized element, and for in loop quantum gravity, a connection, it is only the holonomies. So when you look at this picture, since you have a compact group, then on the compact group you have Haar probability measures. This means that we have now a sequence of probabilities which is considered.
Jean-Pierre, I'm sorry. So you want to say that the space of connection is an infinite dimensional Hilbert space, and you want to have the
it is embedded in an infinite dimensional Hilbert space.
And that means that there are many how to say. I am also kind of analytic, so I know that you can put a different how to say. So space, if I in a sense that means I do not understand that if you have the smooth connection, you propose a Sobolev norm, Hilbert norm, yeah. So that is usually we do is analytic, but if you don't have anything, and you take the only approximation, that the projective limit of the sum of finite approximation, that space. something yes, I don't know that really natural or not. Yeah.
Well, in fact, these approximations are natural because they are done since the 50s. You know, it was when I say Whitney approximation, it is the approximation on spaces of connections. It is the one that is globally used.
Okay.
I don't know. If you look at the literature, it is the only one that is used.
Oh, thank you.
So when I saw that, in fact, first I agreed with this approach because it is well. You can do it is very easy to compute with that, but you know it leads to technical problems. So my first question has been to say, okay, there is this approximation which works and which gives some results, let's say. But there is still this problem of integration, of infinite dimensional integration, which requires many efforts to calculate with. So
okay, thank you. Yeah.
Yeah, it is the pain that you get by using it, which was motivating for me. So, and in fact, when you look at the papers by Adams, these are preprints; they were not published, but he does the calculations and he gets the linking numbers, but he is using a computer. So this can work, but the remark. Let me go a little more in the detail. The technical remark first is that this approximation is not gauge invariant, and when you want to have invariant objects on principal bundles, then your approximation technically needs to be almost gauge invariant, at least almost. I say almost because it must be an approximation which for which at the limit it is not very technical to prove that the limit is gauge invariant. That's the point. And for Whitney approximation, for example, when you change the abelian structure group to a non-abelian one, then you need gauge fixing. It is only by gauge fixing that the infinite dimensional integrals are defined, and the justification of gauge fixing is that, well, we can make gauge fixing because our objects are gauge invariant. But there is no clue on why the limit that we take will be gauge invariant. So there is here a problem with Whitney approximation. So the point that I want to highlight is that when you take one integration step, that is, you integrate the connections along the edges of the triangulation, then you get holonomies, and then with holonomies you get gauge invariant approximations. And if the group is compact, abelian or not, the product, this is a product of probability measures. So when you take the limit, then you get a probability. And these two objects are strictly not corresponding in the space of connections. They are corresponding for one connection. For one fixed connection, you refine the triangulation, then you get the approximation of the initial connection by two ways. First, by the holonomy, which will be really approximate to which can approximate the value of the connection at one point. The Whitney approximation, which can approximate also the value of the connection at one point, but globally there is no estimate that gathers the two. So the open question is that here we have two approaches of infinite dimensional integrals, which are of interest. And the point is that how do we link them? Because after that, we have the Yang-Mills functionals, we have the Chern-Simons functionals, we also have two-dimensional theories and higher dimensional theories, and we need to have a diffeology for which all these theories are in my space of functions f of test functions, and for which we can differentiate from one integral to another. And it is exactly where are our Taylor expansions that we were discussing before the talk. That is, formally, when you take perturbative approaches or Feynman-Cauchy formulas, then you take the Taylor expansions. But the Taylor expansions are, they are formal, you know, not really, but but there are some formal steps. And here we may have a clue for filling the gaps. So it is the point where I am actually, and I think that I don't know what time it is, but I think that I have it finished.
So thank you very much, Jean-Pierre. Yes, very interesting talk. And I think that's your approach to construct is smooth. How to say? Translated invariant differential. The probability measure on infinite dimension space by taking the limit is a new, right? I didn't notice it in the Bogachev book, at least.
No, I don't think so, because this approach is defined in the book by Albeverio, Okron, and Mazzucchi, but only on Feynman on oscillatory integrals, Fresnel integrals. So it is the only book where I found it. It is also in my paper on which I define Lebesgue mean.
So on each year, that is your paper. Can you?
2011.
Oh, so on the
2017. Sorry.
Yeah. So 5 years ago. Okay. So I check also on to so if somebody has a question, please. So if nobody have questions, I check on to ask you a question on you say about the tangents, diffeological tangent space. I think I also read the Christian Wu paper, and then I think that in only nation to define the concept operational tangent space. And we discussed also is Patrick Iglesias Seymour. he says that the natural in diffeology only a covariant object, and tangent space is a contravariant object. So that if only natural, if you define it like an operational factor on the covariant object. And that they also discuss as the notion of the kinematic and the operational tangent vector is only discussed in the book by Grieg and Michal, right?
Yes.
Convenient analysis. So that after that, I think that I cannot remember that the kinematics differential vector is yes, that is not natural object in diffeology, only operational tangent vector.
In some sense, you are right. And actually, there are, to my knowledge, there are three tangent spaces. There is the kinematic one, the differential one, which takes, in fact, the derivatives, the differential operators, and there is also the tangent space defined by the action of the group of diffeomorphisms, which is smaller than the kinematic one.
Okay, that's a group of diffeomorphism.
In fact,
Yes,
the group of diffeomorphism is acting on the space,
right.
so it defines flows, and locally you have a part of the kinematic tangent space.
But this group is how to say that defined very abstractly, right?
Yes, yes.
Yeah.
But I think that it is not natural to have a tangent space, but technically, until someone finds a new formulation for the objects that we consider here in the talk, it is necessary.
But wait a moment, only the Michal and the Greek discuss the question of on infinite dimensional manifold. If you have kinematic tangent vector, it does not integrate, not necessary. And when you consider diffeological groups, that means you only integrate, right? So it considers a smaller class of the kinematic tangent vector space is generated by flow. So that's why they consider also flow, and they separate the two concepts. Yeah.
But local flows are only necessary, in fact, to separate the two concepts. They use local flows because they have charts in Kriegel and Michal.
Yes.
While on diffeological spaces, we do not have charts, we do not have localization. So the things are going even worse.
Yes.
But the point is that we really need to have a good comparison between diffeologies and geometry in measure spaces. That is, on metric space. On metric spaces. On metric spaces, the things are done to have subgradients and so on, and they do not have smoothness, or it is really difficult. But they have some convergence of something. And in diffeologies, we cannot have that. So the comparison between the two approaches would be nice, especially in this setting of probabilities, because it is a motivating example for metric geometry. And I have to announce two ongoing works. First one, there is a nice class of diffeological spaces that I should call pro-finite diffeological spaces that fit with these cylindrical approximations. That is, there are projections, nice projections with sections into finite dimensional manifolds. Typically R infinity and so on, and its subspaces and so on. So on this class, we are actually investigating the what can be simplified in tangent spaces and so on, because apparently we have done it, for example, for jet spaces. For jet spaces, and when you consider differential relations, then you can define safely the tangent space on the full space as in both way, kinematic or by derivations, it gives the same space. So it is a question actually that we are looking at with Enrique Reyes. It is that it should work for these pro-finite spaces. And a second point is that when we want to differentiate on let's say probabilities or means, or we have to take into account that these are already parts of dual spaces. That is, we have an underlying space on which we do not say anything. And it is another work which is actually in progress with Ali Reza Ahmadi, on which we consider diffeologies on Borel algebras.
So I'm looking forward to your new lesson with your co-author on the Borel algebra. Yes, that you already promised in April, right?
Yes. In fact, we thought that we would have finished in September, but we get diffeologies which are on which Boolean operations are smooth. We get Fomin differentiations. We get also Hadamard differentiation for shape analysis. But we need again to clarify some things. But I can announce that we have diffeologically some nice properties.
So thank you very much, Jean-Pierre, for exciting talk. If nobody has more questions, so let us thank the speaker again. Yeah. So it close